right over there. Let me see. It's recording?
Yep.
So if we have a \n, we're going to put it inside the double quote. What about if I don't have a double quote? If I have a C out, I'm going to put some stuff on it, right? I can actually put bunch of these things together. I don't have to put the C out, C out, C out. As far as I don't have a semicolon over here, I can put a bunch of these things right after each other, one semicolon at the end. I don't have to write C out, C out, C out. And I can put an ENDL anywhere I want. The \n can be middle, beginning, or end of the sentence that I have. So if I have C out, I can put the \n at the beginning, I can put it in the middle, or I can put it at the end, whenever I want to do. So that's going to give me a carriage return. So I can put it in the middle of it. What else? Any other questions that you might have when you were doing your work? Any questions on the compiler? So we all have done the assignments and they're all done. Okay, good. Today I'm going to be talking about the computer science book. So for now, what I'm going to do is I'm going to talk about the computer science book on Mondays. And I'm going to talk about the C++ on Wednesdays till we see what we're going to do. Once again, if you do not have the current version of the books, it is on you to figure out the assignments. Somebody sent me an email to send him assignment. I cannot do that. You got to figure out. If you buy the cheaper version, you got to work for it a little bit. Okay. So I'm going to talk about this one first. Is going to go to the chapter 0, general concept of the computers, and then we go to cover chapter 1. So we're going to talk about the algorithms. We're going to talk about the origin of the computing machines. The science of algorithms, that hopefully we're going to start on these things and you take it with you to go through other classes. The outline of our study and the social repercussion. Okay, so when we talk about algorithm, is a set of steps that defines how a task is performed. So before we actually start writing the program, we have to sit down and figure out how we're going to write that program. So for that reason, we do not have the computer on. We got to write it down on a paper or have some other application on. We are not going to be writing program at this time because we are thinking about problem solving and how we're going to write it. We are not going to be writing programs because when I'm writing the program, my main focus is what? How to make my program work. And when I'm thinking about how to make my program work, I'm not solving problems on the actual algorithm itself. So the program is a representation of our algorithm. We're going to take the steps of what we need to do, and we're going to write the code for it. And programming is the process of developing a program, and software is programs and algorithms, and the hardware is the equipment. So we have an algorithm that we created for what is that? A magic trick. So it got a step 1, a step 2, a step 3, a step 4, a step 5, and 6, which is broken down to other steps. So when you're writing a program, this is what you're going to do before you actually write your code. You're going to write down the steps of the things that you're going to do. So it came way before all these things. So when we had the long division algorithm, we had some other algorithm that was there before the steps of what we were supposed to do, things. So in early times, remember, the computer only understands the zeros and ones. So somehow we have to store our stuff in zeros and ones. Early on, they were doing this on a punch card. So there was some cards, actually, I came to this country 1977, and they were using the punch card in the university for the registration. So we would go and pick up the punch card for the course that I wanted, and then take it to the computer, and they would fit it in there with a punch card with my information on it. So it would be a hole in it for on, and the no hole means off. Zeros and ones was stored like that. So early computers, the Bell Lab, that was part of the AT&T at that time, started creating some mechanical relays. And they had the vacuum tubes. So it was a room about this size. The computer was about the room of this size. And it was working with the vacuums. So a system admin was a guy with lots of vacuum tubes and changing the vacuum tubes, and that's what his job was at that time. And that's a computer with, I think, 2 megabytes of memory. So personal computers came along in early 80s. The people who want to play games at that time, believe it or not, on those computers. And then they start using it in the business environment. And then we got to the internet, World Wide Web. In the middle of the 80s, when I was going to school, we did not have internet. My instructor came to the class and said, you know what, somebody came along with something that if you click on it, you can go to another page. We did not have that one in the mid-80s. Search engines came along, and we got the smaller footprint of machines who can do a lot more than what we had before. So when we're talking about computer science, is the science of algorithm, draws from other subjects like mathematics, engineering, psychology, business administration, and I guess psychology 2 times. So when we are looking at the questions for the computer science, first of all, we have to ask which problem can be solved by algorithm process. Can we actually solve these problems or not? And then how can algorithm discovery be made easier? So what can we do about it? How can techniques of representing and communicating algorithm be improved? And the characteristic of different algorithm. So we have a job for software engineers, computer scientists, to constantly working on these algorithms to make it work better. So it is not like just I'm going to write a program. I'm going to write a program that's going to be a very efficient program, and it's going to do the steps much better, so the program is going to run faster and more efficient. So how can these algorithms to manipulate information, how can algorithm be applied to produce intelligent behavior? And more we see that we can make some decision making based on the computer programs. So if we put the algorithm in the middle, we have limitation, we're going to have the application of algorithms, we have analysis of algorithm, discovery, representation, communication. So we're going to start chapter 1. We will talk about the bits and the storage, main memory, mass storage, and how we're going to represent the information in the bits and the binary system. Remember, the computer only understands zeros and ones. So anything that we want to communicate with the computer, it has to be turned into the zeros and ones. We're going to talking about the storing integers, fractions, data compression, and communications error. Okay, so when we talk about the bit with this 0 or 1, that's all we're going to have. It's just a light switch, on or off. And actually that's what it is. The electricity has electricity, doesn't have electricity. So what do we have to present in these zeros and ones? We're going to have numbers, we're going to have text, we're going to have images, sound, and other stuff. So anything we talk about digital, that is going to be in 0 and 1 format. So so when we're talking about digital photography, or we're talking about the movies which are digital, that is going to be turned into the zeros and ones. We are talking about Boolean operation. Boolean only has two answers. It's going to be either true or false. So we're going to check the condition, and we're going to answer it, or we're going to get the answer of true or false. So we're going to be looking at a specific operation, and, or, XOR, and not. We're going to be using some of these things inside of programming, and for those who are going to computer engineering, electrical engineering, they're going to be using these things to create circuits, and so they're going to spend more time on these things. So for the AND, both condition has to be true. Remember, in the binary, I do not have anything else besides 0 and 1. The highest number I can go is 1. I don't have 2 or 3 or so. So I can have 0 or 1. So if we accept the 0 is false, 1 is going to be true. That's the two number I'm going to have. So for AND to work, both condition has to be true. So I'm going to tell you, you have to do assignment 1 and assignment 2. That means you have to do both of them to be acceptable. The OR on the other side is going to be either 1. So I can do one or the other one, or if I really want to be I don't know, exciting, I'm going to do both of them. So either way, so as soon as I see one of them is done, I'm okay with it. So that's the OR. XOR, it says, you know what, when I tell you I only need one of them, you should do only one. So if you do both of them, you're still failing. So XOR is going to be asking specifically for one or the other one. So the whole computer system, electronic circuits are based in these things. So they have a gate that's going to compute these things. So we're going to have a small circuits created with this. And then we're going to have this ones. There is a class called Logic Design. It's going to be only offered in our department on summers. Dr. Wilkerson teaches that, and he's very passionate about this class. I suggest people to look into that class if we have a summer session. So that is going to be covering these things. So For the graphical representation, this is going to be called AND. So both of these has to come as 1 to have the output. So you can have electricity on this one, electricity on this one, or you can say on, that's going to be on. So that is going to be true or false, you can call it. The other one is OR. So as far as I have one of these true, the whole output is going to be true. The only time that's going to output is going to be 0 if this one and this one is false or 0. In this case is XOR. Either one of them should be 1. They cannot be 1 at the same time. If they are, I'm going to get the false. The NOT is going to change it. If I have a 0, it's going to be 1. If I have 1, it's going to make it 0. So the whole logic of a circuit is going to be created with these things. A flip-flop is a circuit built from gates that can store 1 bit. So it's going to store 1 bit. That way it can use it. One input line is used to set its stored value to 1. One input line is used to set its stored value to 0. So we're going to use this 0 and 1 to get, while both input lines are 0, the most recently stored value is preserved. So that way we can have some values before we start. So what's going to happen if I have a 0 over here for the input on the bottom one? There's going to be 1. 1 is going to go here. It's going to be waiting for another 1 to come out of this way. So we should have something over here. So as far as I have a 1 here, this is an OR. So as far as I have a 1 here, it's going to give me a 1 over here. So 1 and 1 is going to give me a 1, and this 1 is going to go here. So that's a simple flip-flop. The whole circuit design is going to be a bunch of these things connected together. So in this case, what do we have? We have a 1 here, we have a 0 here. So the 0 is going to give me a 1 over here, right? This 1 is going to give me a 1 no matter what, because this is an OR. It doesn't matter what it is here, it's going to give me a 1. So I have a 1 here, and I have a 1 here. 1 and 1 is going to give me a 1, right? So what's going to happen if I have a 0 over here? That's going to give me a 1. That the 0, which already had a 1 coming this way. So I have 1 and 1 is going to give me 1. 1 and 0 is going to give me 1, and this circuit can keep going. So we're going to put a bunch of these things together to create a circuit, and this one means they are not crossing each other, they just go over each other. It doesn't cross each other. Okay, so the computer understands zeros and ones, but if we put all these zeros and ones together, it's going to make a long strings of zeros and ones. It's going to make it very hard to understand. So we are going to be using hexadecimal, which is base 16. So when we're talking about hexadecimal, that means it's going to be base 16. So if I have base 10 that we are using daily, that's going to be what? We're going to use base 10. That's going to go from 0 to 9. All right? A single digit is going to be from 0 to 9. I don't have a single digit for 10. So when I go after 9, what's going to happen? I'm going to move to the left, and I put a 0 next to it. So that is my 10 in base 10. That means I have a single digit up to 9, and then I'm going to go to left one time, and then it's going to be 0. So if I have 237, that's going to be 1, that's going to be 10, that's going to be 10 to the power of 2, which is 100, right? So 7 times 1, 3 times 10, 2 times 100. Now, if I go with the base 2, I cannot have 2. I'm going to have a 0 and 1. So after the 1, I'm going to go to the left and add a 0 here. This is going to be my 2. Okay, so for base 2, if I have 1, 1, 1, 1, it's going to be 1, 2, 2 to the power of 2, 2 to the power of 3, which is what? 1, 2, 4, 8. That's the way we're going to calculate. 1 times 1, 1 times 2, 1 times 4, 8 times 1. Now, if I have base 16, that means I'm going to go from 0 to 15. Okay? So, I don't know how to put 15 in a decimal format. So, after 9, I don't have anything in decimal format. We're going to use A, B, C, D, E, and F. So A is going to be 10, B is 11, C 12, 13, 14, and 15. When I go after that, what's going to happen? I'm going to go to the left, and I'm going to put a 0 in there. This is going to give me 16 in base 16. So every time I'm working with the base 16, what's going to happen? If I have 2, 3, 5, first one multiplied by 1, next one multiplied by 16, next one multiplied by 16 to the power of 2. So that's going to give me a hexadecimal, this is going to give me the binary, and this is going to give me the base 10. Now we're going to practice on how we're going to move around between these ones. So I give you an example that you're going to be working on. So this one, it says 1 0 1 0 0 1 1. So if I want to use that one, so if I have 1 0 1 0 0 0 1, I'm going to multiply this by 1, 2, 4, 8, 16, 32, and 128. What happened? 1, 2, 3, 4, 5, 6, 7. So I have 64 and 128. So I'm going to write it again. 0, 1, 0, 1, 0, 0, 0, 1. It's going to be 1, 2, 4, 8, 16, 32, 64, 128. So 1 times 1 is going to give me 1. 16 times 1 is going to give me 16. 64 times 1 is going to give me 64. If I add these things together, pardon me?
It's 81.
Thank you. So this one in the binary is going to give me 81 in decimal. And the way that I'm going to make it to hexadecimal, I'm going to break it down in half, in 4 bits. So if I break this one in 4 bits, I'm going to have 0, 1, 0, 1, and then I'm going to have 0, 0, 0, 1. Okay? So this one is going to give me what? 1. This one is going to give me what? 1, 2, and 4, that's going to give me 5. So this one in hexadecimal is going to give me what? 51. That's hexadecimal. That is my decimal. That's my binary. You got that? Now it's your turn. Let's find something interesting for you to do. That's going to be 1, 0, 0, 1, 1, 1, 0, 1, 2, 3, 4, 5, 6, 7, and 1. So you're going to translate this to decimal. You're going to translate this to hexadecimal. Let me know when you're ready. Thank you. Is that what he said? Thank you. So the main memory address we should be able to get into any area in the main memory. So for main memory, we're going to have some addresses. So addresses is going to be 1 byte at a time. The very first address is going to be 0, and it's just going to keep going up. So if we're talking about 4 gigabyte of address, that means I have the addresses from 0 to 4 billion. That's what it means. So I can go to any specific area and pick up whatever I need from there. So this is the way that the memory is logically designed. It's not actually physically like that, but it's logically here. So if I want to go to address 5, it's going to be right here. Address 7, 9 is going to be right there. So it's going to be a continuous addresses that the program can go to that specific address and pick up whatever it needs. Random access memory is mean just like that I can go to a specific address and pick up whatever I need to. Dynamic memory is the volatile memory. That means when I turn off my computer, everything that I had in the memory is gone. Nothing stays in the memory. We are using the metric system for this: kilobyte, megabyte, and gigabyte. Kilo means 1,000, and because the base 2 does not get to 1,000, we just go over. So we go 1,024 bytes for kilobyte. Megabyte, which is the mega means a million. So for a million, we're going to have 1,048,576, and for gigabyte, we have 1 billion. So the CPU is going to be looking only at the main memory. CPU does not look at any other data, any other places. It only looks at the memory. So anything else to the CPU is secondary. CPU says, you want me to do something, put it in the memory. I don't care where you bring it from. We have to save our stuff somewhere because we know that the memory is going to be deleted when we turn off the computer. So we're going to put our stuff in a hard drive, in a flash drive, in a CD, DVD. Those are all called secondary storage. And of course, we have our main memory. So we can, the magnetic system are the one that they were using magnet. So if it was magnetized, that means it was on. If it was not magnetized, then it was off. 1 and 0. Optical was using the optical system for CDs and DVDs. That's what we are using right now. And then we have the flash technology for a flash drive and SIM card. So with the disk, we okay. Do you know the difference between logical and physical? When we say logical, what does it mean? That means abstract. What does that mean? That we are saying it does exist, but in reality it does not exist. So when we have a name, in real life, name doesn't exist. We're just calling somebody with this name, right? The name doesn't exist. That's a logical thing that we're going to do. We are agreeing that this person name is this one, or that person's name is that something else. But it doesn't exist. But a person does exist in the world. So physical means that physically exists. Logical means we just say it's there, but it's not physically there. So when we're looking for certain addresses in a disk, we are going to logically divide the disk in two things. One is called the track. The other one is called the sector. So if I have a CD, I'm logically going to divide it into sectors. Okay, I call these things a sector. And then I'm going to have some tracks. Once again, these are not actually on the CD. We are assuming that's going to be there. So for me to go to a specific address, I have to go to a specific, if I want to go here, I have to go to a specific track and a specific sector. Okay, remember the sectors are the small pieces and the track are the round ones. So for me to be able to go to a sector, then the CD is going to be turning. CD or DVD is going to be turning. So if I have, let's say I have a head over here. So the CD is going to turn for me to go to the specific sector, and then this arm is going to go back and forth to find a specific track. And the amount of information that's stored right here is exactly the same amount of information that's stored over here. So it's the same amount of the information. So if I am watching a movie and I want to go to the next section, when I click the fast forward to the next section, it's just going to jump to the next address that's going to find a sector and a track to start reading it from there. So if I'm here, then it might jump to this one, or over here to go to the next address. So I have the arm that's going in and out. Actually, we have a hard drive here. If you guys want to look at it, can you see this over there? Oh, we can see it. Okay, so the arm is going to go back and forth to go in there, and the CD is going to be turning to find what? Sector. And then we're going to be, the arm is going to go in and out to find track. It's magnetic tape, so this head over here is going to be reading whatever was magnetized on the tape. It's still up to date. The magnetic tapes are the cheapest storage we are using in industry to do the backup, because it's the cheapest still, and we can put a lot of things in there. We're still using the magnetic tape for backup. So if I want to find something in a magnetic tape, I have to rewind it all the way to the beginning and start searching. That's why they call it sequential. I cannot jump in the middle and find something in the middle. Versus the random access is the one that we can jump into a certain address and start reading. So for example, on the CD and DVD, I can jump into a specific sector and track and start reading. I don't have to go at the beginning and search for it. Any questions so far? Okay, so we are talking about the file is a unit of data stored in the mass storage system. So when we are saving a file in a hard drive, the file name is going to be associated to the address of that file in the hard drive. So the hard drive is going to have some addresses that I can randomly to go to any address I want. So I can just jump to any address. So I'm going to look at the file name that's going to be mapped to an address, and I'm going to jump to that address. So if I am looking at the hard drive, for example, it's going to be 2 to 3 CDs on top of each other. And I'm going to have the arm. Remember, the arm is the moving part, and the moving part is always the slowest part in the computer. So they have this moving part to go in and out. So if I want to write in a hard drive, I'm not going to be writing one file. I'm going to break it down. I'm going to write on top of this, on the bottom of this, top of this one, on the bottom of this, top of this one, bottom of this. So instead of moving the arm too many times, I'm just going to be writing 1, 2, 3, 4, 5, 6 places at the same time. And when I want to read, I do the same thing. I'm going to go with the file name. That's going to point me to a location that I can read in multiple places. While I'm here, I can talk about something else. So in a hard drive, if this is my hard drive and I have a file that, let's say, is starting with this address, I'll call it, I don't know, 25679. This is my file name. Okay? So if my file starts over here, very first bit is going to say if this file, or 1 byte, doesn't matter what we're going to do, is going to say if this space is available or not available. So when we delete a file, it's just going to go change this bit from 1 to 0, saying that this space is available. So next time when I'm writing, it's going to go and write on top of this file that I had. We don't have any eraser in the hard drive to go erase everything. So it's just going to say this space is available, and that's why if federal, FBI come to somebody's home, they can go figure out what was on the computer, because they can read the stuff. It's already on the hard drive. It just says this is available. Yes?
So when you use something on a computer, that doesn't mean this thing is destroyed. You still can find it.
That's correct. So the question is, when we are deleting something in the computer, it is not physically deleted. It's just going to say this space is available. So next time you're writing, might go to that place and write on top of that one. So for those softwares that they are doing the deleting of the hard drive or cleaning hard drive, they actually go and write bunch of zeros and ones on top of whatever you have. Okay, so next is the buffer. So the buffer, we need the buffer because the devices that we have, they are not on the same speed. So before, if I printed something, because the printer is, remember, printer still has a moving parts, and that's going to be much slower than the computer itself. So if I would have print something, I have to sit and wait for the print job to finish before I can do anything. And they decided they're going to put this buffer in it. The buffer is between the devices. So now I'm not going to send my print job to the printer directly. I'm going to send it to the buffer, and the buffer is going to send it to the printer in their own pace. You have seen this when you are downloading a movie or you are streaming a movie that you want to watch it. So they have a buffer that's going to bring the things on the buffer, so while you're watching, it's going to take it away from the buffer. If you don't have that one, then the movie is going to stop, or if my buffer is full or it doesn't come in, it's going to stop. So that's why we need the buffer. That's going to be between devices that they are different speed. Same thing goes with the graphic card or any other devices that's in that matter. Okay. Now, everything on the computer is zeros and ones, but we don't want to deal with it as a 0 and 1. We want to work with it as English character. We want to use numbers in an English system. So they came up with this table that's called ASCII table, and this ASCII table is going to be like a map that's going to take the 7-bit out of the 8-bit 1 byte, and it's going to map it to everything that we're using on the computer. All the characters are defined. I mean, the character, I'm talking about space, carriage return, I'm talking about the bell that the rings when you anything that's on the computer is going to be mapped to some numbers in 7 bits in the ASCII, and of course 8-bit, which is the extension for ISO, and 16-bit in Unicode that has a lot more in it. So if I go on internet and I look for ASCII table, I'm going to pick up which one is nicer. So we are starting with the 0, which is null, which is nothing. And my favorite one is number 7, which is a bell. So if I print number 7, it's going to ring. And then we got the backspace, horizontal tab, and all kind of tabs and all those things here. And if you go to this column over here, you can see that we have 65 of decimal, which is 41 of hex, and that's going to map to capital A. So if I have 8 bits, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. So if I have 8 bits, remember this is 1, 2, 4, 8, 16, 32, 64, 128. Now I want to create 65. How do I make 65? 64 plus 1, right? Everything else is going to be 0. 1 and 1 here is going to give me 65, right? 65 was what? 65 was A, capital A. Okay? So the 32 is the shift character. So if I put that one on, that's going to add 32 to 65, which is 97. That's going to be lowercase a. That's why when we're sorting our files in a directory, the capital comes before the lowercase, because in the ASCII table, the capitals are smaller than the lowercase. That is a 32. Okay, what's going to happen if I add 1 to this? So 1 plus 1 is going to give me 0 carried 1. 1 plus 0 is going to give me 1 here. So if I add 1 to 65, it's going to give me what? 66, that's going to be B. If I add 1 to 97, that would be 98. That would be lowercase b. Okay, that's the way that if I put capital A on my keyboard, it's going to be translate to 01000001, and vice versa. If that's coming from the computer, it's going to be translate to capital A on my screen. Any question on the ASCII table?
Which language are you using this table? Assembly or machine language? I'm sorry, assembly?
No, this is a standard for everybody. So in the C++, the language is using numbers. So I can, in my C++, take a number of 65 and then print it as a character. That's going to give me A. And if I print the number of A, it's going to give me 65. So it's stored in the computer as a 65. So this is a standard that everybody's using it.
Do we have to remember this one, memory? Which one?
Yeah, why not? You can memorize this one by tonight, right? No, you don't have to memorize it. That's why we have the table. We're going to look it up. So we have capital H. What the decimal number is this? 72. And the lowercase e, and then we have the period over here. What is this one? $46. So we are using binary, which is base 2. That means I don't have number 2. Base 2 doesn't have number 2. It has zeros and ones only. So if I am going to be, so if I have 1, let's say I'm going to use only 4 bits. Okay? If I'm using only 4 bits, if I add 1 to this, what's going to happen? it's going to give me 0, 0, 0, 0. I only have 4 bits, so it's not going to go outside of this. So what was this number to start with? 8 plus 4 plus 2 plus 1. 15, right? So what did I do right now? I add 1 to 15 and I got 0. That is the overflow. When we say truncation, that means we are using, so we are adding some numbers that's going to come up with a different result. Remember, we have a limited space in the memory, so if we go outside of our space, some other things are going to happen. C, C++, Java, they try not to crash your program, so what they're going to do, they're going to write on top of the other one. And we're going to see that later on. So everything is digital, it's going to be translated to binary, means zeros and ones, and then we're going to have some schemes to keep those zeros and ones to figure out what it is going to come up. So when we have the bitmap for the picture, we have pixel, we have RGB, and we have different system for the audio, for the video. So the traditional decimal system that we are using is base 10. That means for a single digit, I can go from 0 to 9. I cannot go to 10 for one single digit number. So for the decimal, we go with the power of 10. So it's 10, 100, 1000. For the base 2, we go with the power of 2. So this is something that you have to know for your test, how to go from one to the other one. So I have base 10 is 375. I'm going to multiply this by 1, by 10, by 100. This is base 2, 1, 2, 4, and 8. So 8 plus 2 is 10 plus 1 is what? 11. What is 11 in hexadecimal? B. So this is B in hexadecimal. It is 11 in base 10. Good? It's not 11 in base 10? Are you guys falling asleep? Wake up. So we're going to multiply by 1, 2, 4, 8, 16, and 32. In this case, we got all of these add up. It's going to give me 37. Okay, if you want to go backward, for the base 2, we're going to divide by 2. For the base 16, we're going to divide by 16. For base 10, we're going to divide by 10 to find the numbers going the other way around. Okay, so going from 13, I want to go to base 2. I'm going to get the 13 divided by 2. I get 6. I get the 6 divided by 2. I get 3. 3 divided by 2. I get 1. 1 divided by 2. I get 0. So I put these things next to each other. I get 1, 1, 0, 1. That is going from decimal to base 2. So if I want to go hexadecimal, 13 divided by 16 is going to give me what? Yes, 13 is going to be just the D. Because 13 doesn't, then we cannot divide 13 by 16. So if we're doing the simple addition, 0 plus 0 is going to give me 0, 1 plus 0 is going to give me 1, 0 plus 1 is going to give me 1, 1 plus 1 is going to give me 0, 1, or 1, 0. So what is this? 2. Okay, now we're going to go to fraction. Remember, everything in the computer system is zeros and ones. So even the fraction is going to be in zeros and ones. So it's going to define logically, there is no period anywhere. So it's going to divide these things and says logically over here, this is going to be 1/2, this is going to be 1/4, this is going to be 1/8. So it's going to put the 1/8 plus 1/2, that's going to give me 5/8. And of course we will have 1, 2, and 4 over here. That's the way that the computer is going to figure out the fraction. 2's complement. The computer doesn't have subtraction, but it knows how to do the negative numbers. So the 2's complement means getting a number and change it to its own negative number. So there is 2 ways of doing it. The way that I am used to do it is I get any number 1, 0, 1, 0, 1. I just change the 1s to 0, 0s to 1, and then I add 1 to it. So what is this in decimal? 1, 2, 4, 8, 16. 16 plus 4 is 20 plus 1 is 21. So this is the representation of negative 21. Of course, this is not a good, let me put a 0 over here. The reason I put the 0 over here is if it's assigned, the beginning of this is going to be positive and 1 is going to be negative. So this is the representation of negative 21. That's the representation of 21. Your book, you does it a little different. So the way that your book does is it's going to start going to the left and copying everything till it gets to the 1. After that, it's going to change everything. So it's going to do 0, 1, and then as soon as it hits the 1, it's going to change everything to the left of that. So it's going to be 0, 1. So that's 2 ways, whichever you are comfortable with, you can do it. So what is this number in decimal? 6. So this is the representation of negative 6. That means what? If I add this number to this number, I should get a 0. 0 plus 0 is going to give me 0. 1 plus 1 is going to give me 0 with carry 1. 1 plus 1 is going to give me 0 with carry 1. 1 plus 1 is going to give me 0. So these 2 numbers I added up together is going to be 0. Do we have any questions?
Are we going to do this in the test?
Yes, you will do this in the test. So for the computer to know how to subtract, it not actually knows how to do the subtract. It only knows how to add. So it's going to change the positive number to negative numbers, and it's going to add negative numbers together. So 3 plus 2 is going to be like that. Negative 3 plus negative 2 is going to do the 2's complement and then add them together. 7 minus 5 is actually 7 plus negative 5. So that's the way the operation is happening underneath of all these things. So you can see that negative 1, of course, it's using 4 bits over here. So how are we going to do the decimal points? That's another way of doing it. So it has a sign bit, which is the most significant bit. Then we have the exponent, and then we have mantissa. So 2 and a 5, 8 is going to be 1, 0, 1, 0, 1. That would be the 5, 8, which I did it earlier. And then it's going to take the least significant one out, and it's going to be turned into 1, 0, 1, 0. And we got to do some practice on this to make a little more sense. So the last thing that I want to talk over here is about the data compression, because the files were getting big and the transfer of the files were hard to do, or they decided that they're going to find a way to make the files smaller. And that's what the compression started. So is there anything that we can take off or reuse in there so we would have a less space? So different way of compression. And of course, there is some algorithm involved with that, and how they're using it and how they revert it back. So if we get the image and we compress it, we have a GIF, JPEG, and TIFF. So there is some algorithm in there that is going to go and find things and figure out how to compress it. So for example, if I have 5 pixels right after each other with the same color, I'm going to put one and something that's going to tell me that the next 5 pixels is going to be black or green or whatever. So it's got some way of compressing it. So if there is a picture and it has, I don't know, 25 pixels with the same color, maybe I don't need to have 25 of the same color. I got to find a way to show one pixel with one color and then say this is going to expand to 25. So it's going to go horizontal, vertical, whatever it is. That's going to be the way that the JPEG or GIF or TIFF is going to be doing it. That's why they cannot understand each other sometimes, because the way that they compress and uncompress is going to be different from each other. Same concept goes with the MPEG and MP3. That is the way that they're going to do it with the audio and video. That's why they're trying to get to the standard. So every time we come up with the new technology, you're going to be 2, 3, 4 different types, and one of them is going to take over the industry. And of course, the company who was doing it makes a lot of money. The rest of them got to go do something else. Okay, when we're sending things through the internet, there is a high possibility that we lose things or we get damaged, and that's very, very common. So one way is to check the bytes that's coming in to say if this byte is a good byte or not a good byte. So for that, there are some schemes to do it. One of them is called the parity check. That's even versus odd. This one is going to 1, 2, 3. So this is the odd parity. So this one is going to be sure that this whole thing is going to be odd. So when it gets to the other side, it's going to say 1, 2, 3. That's odd. So this is good. It's never going to look at the first one. It's just so in this one we had 1, 2, and 3. It was already odd. We didn't have to put anything in here. So every byte that goes across the internet in this system is always going to be odd parity. That means it's always the number of the bits are going to be odd on one byte. So there is an error code check that's going to check for the error, and it's going to find it. You have an assignment to play with this to figure it out. So this one is looking at the smallest distance, and that's the one that is going to find the problem with, and it's going to figure it out. Questions on this? So the assignment 2 is already on Blackboard. That would be for this book, and you got some assignments, and you have what till Monday? You need more time?
Because I'm waiting for book.
Monday, Sunday, what's the difference? I'm going to go over your programs that you have done so far, so we'll be sure we are in the right page. Once again, if you want to get hold of me, please send me an email, the school email instead of the Blackboard. I'm trying to make a habit of checking Blackboard, but I'm not checking it every single day. I do check my Pasadena email every single day, few times a day. So if you want to get hold of me, that's the way to do it. And remember, I have my office hours and lab hours posted, so you're more than welcome to come and see me on my office hours.